This is Phil Koopman with a tutorial on times, dates, time zones, and other general forms of time-based madness. Everyone has asked someone else what the day is or what the time is. What we're going to find out in this tutorial is that tends to be a trick question. There are plenty of date and time issues, and writing embedded software to keep track of date and time is incredibly tricky. Beyond leap years and leap seconds and daylight savings time, you also have to deal with where you are, what time zone you're in, the local daylight savings time rules which change, local display rules, and so on. Reconciling time is tricky, and even if you get all the time zone and timekeeping stuff straight, synchronizing two computers so they can coordinate is very difficult because they never exactly agree on time, they only approximately agree. And so we'll talk about all these issues. The most frequent ANDing patterns for date and time that I've encountered are, number one, the day for daylight savings time is hard-coded into the system, and then some legislative body changes it. Number two is time is kept without handling time problems such as daylight savings time, time zones, or moving the system around. And number three is that internationalization has not been considered, and it turns out a lot of the world does not speak English, and even within English-speaking countries, a lot of the date and time rules differ depending on where you are. Let's start with the basics of just trying to keep track of what time it actually is. There's some terminology we'll build up, and then we can explain some of the issues. The first term is local time. That's the time based on the local microcontroller clock rate. So your microcontroller has an oscillator that might be at 8 megahertz or 32 megahertz or whatever, some number, and it oscillates back and forth. But every oscillator in every microcomputer has a slightly different rate. And so there's a local time based on that clock rate. Generally, every so many clock oscillations or CPU cycles, there's a timer interrupt, and then there's software that keeps track of the time from there. I said the oscillator is not perfect, so there's a local time, which is the time your system thinks it is, and there's a drift rate, which is how different your local passage of time speed is versus a perfect clock. For example, 0.002% is 0.00002 seconds per second drift rate. That means that every second that passes, you might be 0.00002 seconds wrong. That's not a lot of time in 1 second, but there's a whole lot of seconds in a year. This is actually a somewhat common type of drift rate at that rate, and at the end of the year, you can have several minutes of inaccuracy in your clock. Now, what do I mean by accuracy? Accuracy is the local clock versus perfect time. For example, if you have a multi-node system, node number 2 is 1 second slower than true time, and so its accuracy is off by 1 second. Every local clock has a different accuracy, but all those accuracies are with respect to whether or not it's on top of a universal notional perfect time or whether it's off. It's common for embedded systems to have multiple computers coordinating, not necessarily even in the same time zone, and so the time difference between two clocks is the offset. So for example, node 1 may be 3 seconds faster than node number 3. This offset has no idea what accuracy. Both clocks could be an hour off from perfect time or 10 hours off from perfect time, but as long as the two clocks agree within 3 seconds, maybe that's good enough for your application because you're interested in agreement rather than running a clock display. Every pair of local clocks within a system has an offset. Well, that sounds like it could be kind of chaotic if the offsets are completely random, and so there's the notion of precision. Precision is the maximum offset between any two local clocks. And so if number 3 node is the slowest in the system and number 1 node is the fastest in the system, the precision is their offset, which is 3 seconds. There's only one precision value for a system because it's a global across the system kind of number, whereas every pair has an offset. The notion of precision and accuracy are decoupled. Again, precision has to do with whether or not all the clocks in a particular embedded system agree with each other, and accuracy has to do whether that agreed upon value is actually representative of actual universal notional perfect time. Regardless of whether you care more about precision or accuracy, you need to do some sort of clock synchronization. and this is a notoriously difficult problem to get exactly right. The question is, if you have a local clock that's incorrect, either because it is inaccurate or it has drifted too far away from the other clocks in the system, you need to fix it. Typically, you can only do this periodically because fixing a clock usually requires some sort of network message, and you cannot saturate the network with timekeeping requests. So you usually get some sort of periodic access to a clock server, and either it's a clock server that knows the global time, or it's a node within a distributed system that somehow has been asked to make sure all the clocks are in sync. There are distributed protocols as well, but that's beyond what we'll talk about. If you have a local clock that's wrong, you have a choice to make. How do you fix it? And there are two ways to fix it. The first way is state correction. State correction is fast forwarding or reversing to the correct time. So if you have a watch that you want to change or a digital clock you want to change and you use the go forward, go backward buttons, that's state correction. You basically jump forward or backward. That's easy to implement, but the problem is that any underlying system operation has just had a potentially huge discontinuity in time. If the system is in standby mode, maybe that's okay, but if there's some sort of control loop or real-time operation or date-stamped records going on, that state correction can be a problem, especially if you go backwards and you have duplication of the same date timestamp at different actual times during execution. The alternate way to adjust time is to use rate correction. In rate correction, you don't actually fast forward back or forward. What you do is slightly speed up or slow down the local tick rate. So for example, if you have a software interrupt that's adding 53 to the local time every time there's a timer interrupt, maybe you change it to be 54 and it will run the clock a little bit faster before it's time to increment the second. Or you change it down to 50 and it'll run the clock a little bit slower. It'll take more ticks before it's time to update the clock. Rate correction permits the time to be slightly incorrect for a while you're catching up. But the good news is that you were already bad to begin with and you're just slowly making things better. In practice with rate correction, it's a little trickier because you're actually running a clock rate control loop. At first, you have to catch the clock up to real time, but then once you have basically a match to externally validated time, you have to change the rate to sort of home in on the correct rate rather than overshooting. If you're on the internet, usually what people use is network time protocol. That's a time management service that is designed to keep all the clocks synchronized everywhere across the internet, and it does things like account for estimating the latency of network packets to and from time servers of the internet to get pretty good accuracy as well as good precision. It's complex, and the behavior depends upon options, so this is something you really need to study before you use. If you have small processors or don't have internet connection, then you're going to have to look up a different way to do time service. Some protocols have this built in. Other protocols, you have to go find some software packages and do it yourself, and it can get complicated. So this is something to consider when you decide to go on your own solution, what your plan is for clock synchronization. Once you have your clock synchronization set, now you have to decide if you only care about precision, in which case it's not so bad, or if you care about accuracy. As soon as you care about accuracy, you're asking the question, does my system's clock match the outside world's time? And that gets very tricky. Time zones were originally created in the UK for rail schedules. They had a problem that each train station on an east-west line had a different local time because the sun rises and sets at a slightly different time as you go east or west. And they had trouble coordinating train schedules because they had to deal not only with the travel time, but with the fact that every station actually had a different time on its clocks. And so the original time zones were to synchronize clocks across groups of stations. These days, more or less, sort of less, we'll get to that, time zones give you 1 hour differences between different groups at different longitudes. Now, the more or less, the tricky part is it's not necessarily whole hours. For example, India has a time 5.5 hours away from the reference, and Nepal has a time 5 3/4 away from the reference, and there are a couple other places that do this sort of thing. So software that assumes all time zones are exactly 1 hour apart won't work properly in those areas. Another issue is that daylight savings time is an arbitrary government construct. So this is the idea, at least in the Northern Hemisphere, you spring ahead and you fall back. But in World War II, the US went to permanent daylight savings time, calling it wartime. And also in the so-called energy crisis, the US went on permanent daylight savings time. Even within the US, the rules are not consistent. Arizona, for example, does not observe daylight savings time unless you happen to be in the Navajo reservation inside Arizona, which does do daylight savings time. But there's the Hopi reservation, which is inside the Navajo reservation that does not do daylight savings time. So if you pick the right road, you can drive in and out of daylight savings time several times on a single road trip. Another quirk with daylight savings time is that the dates differ by location. In 2007, the US and Europe changed the dates they switched to daylight savings time. So there's a couple weeks in there where one of them is on daylight savings time and one isn't, and all the time differences between the countries change. Also, don't forget that spring ahead and fall back has to do with the local season, and the seasons in the southern hemisphere are inverted to the seasons in the northern hemisphere. As difficult as it sounds to synchronize the current time on clocks, things get even worse if you need to know the local time, meaning the time that has to do with the sun and the stars at your location rather than the convention of whatever time zone you're in. One type of time is solar time, which is based on the mean sun position. Another is the local time, which is the time in your time zone. And so there's a difference between where the sun on average crosses at noon where you are, which depends on your longitude, and the place you are in your time zone. Time zones are referenced to GMT, Greenwich Mean Time, which is time zone 0. And so if you, depending where you are, you're either 1 time zone away or 2 time zones away, or as we saw before, maybe 5.5 away. But the reference for time in general is GMT plus or minus your time zone. The official time is Universal Coordinated Time, UTC. That's a French abbreviation. That's why the letters are in a different order. And they differ from each other based on whether or not there's a leap second, which we'll get to. For practical purposes, for most purposes, people would say GMT as the 0 time zone and then say I'm in GMT plus or minus some number to indicate which time zone they're in. But back to solar time, sunrise and sunset depends where you are. The sun rises earlier the further east you go, and within a time zone, you're going to find out that the sun rises and sets at different times depending where you are in the time zone. There's some particularly wide time zones. For example, Boston to Detroit has a very significant delay between when the sun rises and sun sets in local time. But even bigger is China, which is all in one time zone. And since China's all in one time zone, what you find out is that the sun rises a whole lot earlier in the eastern part of China than the western part of China, and there's a really significant number of hours of difference there. If you have an application that needs to compute when the sun rises and sets, for example, you want to do automatic shades that sort of keep the sun behind the shade while letting light into the room, or you're building a navigation system that depends on the sun and the stars, for example, you have to know that sunrise and sunset depends on where you are, both latitude and longitude, but also your altitude. And the sun angle and the length of the day change every single day through the year as you go through summer and fall. So if you actually want to know where the sun is and do some sort of computation, you have to know latitude, longitude, altitude, but you also need to know that the local time, as I mentioned, was based on the mean sun. That's not the actual sun position. It turns out the sun moves backward and forward at local noon time. Sometimes the sun will cross the noon line before noon, sometimes after noon, and it can be several minutes difference. There's a thing called the equation of time you can look up. Usually you look at something like a nautical almanac, and it will tell you for every day of every year exactly where the sun is compared to the mean sun. And so if you need to know where the sun is, you figure out what your local time is based on your position, and then you figure out what the equation of time is, which is the difference between the mean sun and the actual sun, and that tells you where the sun's going to be at a particular time on a particular day. This sounds complicated? That's right, it is. It's a very difficult calculation, but if you need to know where the sun is, you have to take all this stuff into account. Mobility and distributed systems present another challenge for time. If the time depends upon your location, then asking what time it is requires knowing where you are, or if you have multiple systems, where each one is. A lot of times you need to answer the question which event happened first, and if the two systems are in different locations or the two systems are moving, then it can be kind of difficult just looking at local date timestamps to figure out what happened. Beyond issues with time zones and things like that, there's also the issue of the international date line. Now, the idealized reference is it's a north-south line at exactly 180 degrees longitude, and when you cross it, the day changes. But the reality is a little more complicated because countries don't want the date line going through the middle of one of their main cities, for example. And in the Pacific Ocean, you can see the date line contorts quite a lot. For example, some of the islands that are moderately far east in the Pacific Ocean stay on the same date as Australia and Asia because it's said to make trade easier. Or more subtle but also problematic issue is that some software assumes that there's a maximum of 24 hours of difference between any two locations. But in fact, there's a part of the Pacific where there are two locations across the date line that are 25 hours apart. Some of the potential issues dealing with mobility and time zones are you have a system with multiple users in different time zones, and they have to agree what time something is and which event happened first. You may have a system that moves between time zones because it's mobile, and it may not even move all that far. It may go from one island to another and experience a 25-hour time jump. That move could happen while it's powered on, and it can deal with it, or it might happen when it's powered off, and it has to clean up the mess the next time the power turns on. Also ask yourself, what if the system is turned off during a daylight savings time change? Or even if it's on, there's a common bug that if you're setting the clock back an hour at daylight savings time, you see a bug where it sets it back an hour and then it goes forward and then it says, oh, it's time to set the clocks back, and it gets stuck in an infinite loop setting the clock back, or maybe sets it back twice. So those kind of things are tricky. They only happen once a year, and almost every daylight savings time change somewhere there's a report of some software that got it wrong. So that's something to pay attention to. A best practice for dealing with all this stuff is to keep time with Greenwich Mean Time, or UTC, inside your system. And that way, any two systems are comparing GMT times rather than local times. And that gets rid of all the local time mess for internal timekeeping. You then convert on the fly the GMT to local time if there's a need to display it. And at that point, you add in the effects of daylight savings time, time zones, etc. So that way, if a system's moving around, the internal timing isn't jerked around by which time zone it's in. But you do have to have local routines to be able to convert from GMT to local displayed time. Just to make matters a little crazier, you have to deal with time leaps. Everyone knows about leap years and the fact that the calendar year is about 365 days per year, and that we have to deal with that quarter day someplace. The rule is that every fourth year, more or less, on February 29th, there's an extra day added in, except every 100 years you don't add the day, except every 400 years you do add the day. So 1900 and 2100 are not leap years, and 2000 was a leap year. So a lot of software dodged a bullet in 2000 because they got lucky, but in 2100 they won't be so lucky unless they know the entirety of this rule. It's common for software to have failures on leap year. One of the more spectacular ones was the Zune completely bricked on leap year. You can see the code for the Zune that caused the bug, and it boils down to a missing else. There's a clause that says if days greater than 366 do something, but if days are exactly equal to 366, there's a problem, and the software just wedges. Another issue is leap seconds. The Earth's rotation is not constant, and so UTC has occasional leap seconds added. Every once in a while, an extra second is inserted, and it's a 61-second minute. So the time goes 23:59:00 up through 23:59:59, 23:59:60, that's right, 61 seconds in a minute, and then over to 0 for +1 day. If you have software that assumes that there's always 60 seconds in a minute, that software has a bug because leap seconds will break that assumption. Theoretically, you could have a negative leap second as well. That hasn't happened yet, so it'll be interesting to see which systems break when that happens. Now you can skirt all this stuff by using GMT instead of UTC, but for applications that use UTC, you have to deal with leap seconds. There are also issues that local rule changes can cause time leaps. So if a particular location changes its time zone, or changes the day it does daylight savings time, or makes some other change like that, it can cause a big discontinuity in the local time, sometimes with almost no notice. Yet another category of time leaps is time rollovers. These can appear as a huge backward leap. The most famous one was the Y2K or Millennium bug, where software had 2-digit years and 99 to 00 rolled over and made it look like they were going back 100 years. Now, the common sentiment is, oh, that was no big deal. But that's said by people who weren't there at the time and weren't really paying attention. Huge amounts of money were spent to avoid those problems. In particular, it was pretty common for IT systems such as payroll or timekeeping or scheduling to just do a hard crash when that happened, and they all had to be replaced or put out of service before 2000 to avoid those outages. There's going to be another similar event in January 2038 when Unix cron rolls over, and it's basically the Y2K bug for Unix systems. Another problem is internationalization. Here's an example. What day is 02/03/16? In the US, you probably meant February 3rd, 2016. But in Europe, you probably meant the 2nd of March, 2016. Or maybe you were talking about 1916 because there's a Y2K issue going on. And so what the date notation means and how the day has to be displayed varies depending on where you are. A little more subtle, but just as tricky, is if you're displaying a calendar, the first day of the week could be a Sunday or a Monday, depending on where you are. And there may be even other variants I don't know about. Even moderately recent dates are not necessarily on the same calendar. China has a traditional lunisolar calendar, complete with a leap month, and translating from those dates to Western calendar dates can be challenging. There's a litany of other internationalization issues, and the point is if your system is going to be used anywhere but your home country, these are the kind of things you have to worry about. You have to worry about AM, PM versus 24-hour clock. So some countries traditionally use 24-hour clock, some use 12. The military often use 24, even if it's in a country that usually uses 12, and so on. You have to worry about English versus metric units, and some countries have mixed units, English for some, metric for others. You have to worry about currency signs, numeric notation. Some countries use a decimal as the radix point, others use a comma. You have to worry about character sets. Are you ASCII or are you 16-bit Unicode? You have to worry about keyboard data entry because different keyboards have different layouts. And you have to worry about whether text is displayed left to right, right to left, top to bottom, and so on. A more subtle and potentially very tricky thing is dealing with gender in language. Some languages, not including English, have gender built into different forms of nouns. They have different verb forms depending on how personal or formal you wish to be, and so on. And there's the issue of gender identification. Think hard before you commit to a system which has two boxes. One says male, one says female, and the user is required to pick one of them. If you've watched this whole timekeeping tutorial, at this point, you're probably holding your head and saying, oh my goodness, what do I do? This is all so hard. And part of the point of this lecture was just to let you know that it's a really hard problem and you should not dive in without realizing what you're getting yourself into. The most practical advice is as soon as you need to worry about accuracy at all, what external time is, you should use validated timekeeping libraries that you got from a trusted third party. It's complicated to do this right, and if you write your own code, you're going to make mistakes. Even if you're Microsoft, look at the Zune code. You also need a way to change daylight savings time, time zones, etc. because your system may move or the laws may move out from under your system. Either way, it's going to change how things work when converting internal time to external time. Don't forget that you have to worry about mobility, so your system is likely to change time zones or change time zone rules, and you have to worry about multi-site coordination. In other words, two systems may have to establish a common notion of what time it is and what event sequencing is, but they're in different local time situations. Also, think through internationalization. Getting internationalization perfect is extremely difficult. It's very, very complicated. And so most systems don't try and do that. Most systems just say, look, we're going to support certain things, other things we're not going to support. And now that you've seen all the options for internationalization, it may become more apparent why there are so many systems that operate only in Chinese or operate only in English. The timekeeping pitfalls are plentiful, but at a high level, there's three to really worry about. The first one is, in general, you should not be relying on accurate distributed time for notions of before or after. No matter how hard you try, if two events happen at almost the same time, it may not be possible to really know which one happened first. Another pitfall is putting in hard-coded changeable time rules such as fixed daylight savings times burned into the program or time zones that are burned into the program, because that stuff changes every time a government decides to change it. If you do not have a software update capability, you should at least have a way to disable the automatic time changes to avoid a situation in which a system has automatic daylight savings times that are wrong, so a user has to intervene 4 times a year, once to fix the wrong daylight savings time, once to put in the right daylight savings time, and then 2 more times at the other end of daylight savings to undo it. The last pitfall is people commonly don't even think about internationalization needs. Now, if you decide that you want to have a single version in a single language and a single set of conventions, that's fine. But realize that's the decision you're making, so you're not surprised later on when users express unhappiness that it doesn't conform to their local time displays or language issues or all those sorts of things.